Leading to the committee of Thailand Young Physicist Tournament, my name is Intash Phatanasorn. I'm from Pajiratsalam School, and I'm here to present thinking ruler. For the problem, it said that when a ruler is camped at one end and stuck, it oscillates and emits a characteristic sound. Investigate how the sound depends on relevant parameters. For the keyword, the first keyword is ruler is camped at one end and stuck, and second, it oscillates and emits a characteristic sound. For the outline of the experiment, and this is phenomenal observation. As you can see from the video, the ruler is camped at one end and push the ruler down and releasing it. Let's call the ruler to vibrate and emits the characteristic sound. From the characteristic of sounds, we contain the sound pitch, sound intensity, duration of sound, and the timbre of sounds. The chosen sound parameter is pitch. With the model of beams, we consider a beam of the length L, and the sum of constant, which is density, young modulus, and second moment of area. From the assumption of Euler-Bernoulli beam theory, you need to know. And when the beam is deflected, the normal recombinant distribution on the cross-section is given by the first equations, which same term in the form of displacement functions. We can substitute the state tensor and moment can be calculated. If there's a motion in normal directions, apply the law of motion, and we simplify the equations. If it's free vibration, then the distribution load is equal to 0. Which is something represent an energy dissipation mechanisms, which you can write the damping force into the equation of motions. We assume the vibrations can be separated into the space and time components. We substitute into the beam equations. This use the temporal ODE with respect to time, which governs oscillation and decay of the amplitude over time, and the spatial ODE with respect to this horizontal displacement and this governs the shapes of each vibration mode. There's a generalization of the spatial functions that you can apply the boundary conditions to it. And this estimates the value of the beta constants. So this condition lead into the characteristic equations who look at these discrete sets of numbers. For the theoretical model we have approached is Euler-Bernoulli beam equation with dampings, spatial ODE and temporal ODE. And we have now obtained the final damped first mode wave equations based on the fundamental equations, and we can find the frequency of mode by the angular velocity and the frequencies relationships. For the experimental setup, we have Arduino board. Experimental part, we have sound sensor connecting with the Arduino board, the ruler and the clamp. Come to the P experiment, when there's from the beam theory, the relationship between the deflection and the applied load is given by these equations, and we can find the Young modulus constants of the ruler from these equations. We now use stacker to measure the deflection length. We now plot the graph and obtain the ruler's Young modulus. And here is ruler's physical constant we have obtained. This is our experiment, which is independent variable we want to study is the cantilever length L. Dependent variable is fundamental frequencies, and control variable is ruler physical constants. The result is variable ruler, which is into the spectrums. We have used to analyze the sound spectrums. The highest peak indicate the ruler fundamental frequencies. So the result for the results for each cantilever length, we have studied spectrum is average from 15 measurements, and the blue peak indicate the experimental peak frequency with its fundamental frequencies, and the red peak indicate the theory fundamental frequencies. And there's a graph that shows relationship between the cantilever length and the fundamental frequency, which produced by the ruler. You can see that the blue curve represents the theory curve, and here's experimental data. So the experimental data follow the same trend as the theory, and the frequency decreased rapidly at the L or the cantilever range increase. This consistent with the frequency equation we have derived, and the small difference occurred due to the amplified clamping and the measurement noise. The experiment support the theoretical model of the cantilever vibrations. So for the conclusion, from the relationship between the fundamental frequency and the cantilever length experiment, it's confirmed that the fundamental frequency scale exactly at the inverse of the cantilever length square, and the numerical value are closely with the cantilever beam theory we have approached. And the lambda constant is derived by the characteristic equation varied by the boundary conditions. So this is my background readings, and thank you for your attention.